Yes, the key will tell us about full wave numerical approach for complex waves. So in case if you have any questions, you may ask the question by voice, but please make sure not to interrupt our speaker in the middle of the sentence. With that, this station is yours.
First of all, thank you very much for your invitation. Today's my talk is about full-wave numerical approach for complex leaky waves in periodic and bandgap structure and its application in millimeter wave and optical devices. First of all, I will start with the introduction. In the beginning, I will talk about the method. First of all, about the method, which is applicable for complex and leaky waves. And then I will show how this modal analysis can be used to actually design directive leaky-wave radiation in periodic structures. First of all, I would like to mention that when we are talking about the complex wave number, when we are talking about attenuation constant, commercial software actually, unfortunately, cannot calculate the attenuation constant. But this parameter is crucially important when we actually design the directive type radiation systems for antennas, and I will, if I have time, I will talk also about the optical application in optics about all optical logic gates. And I will also show the realization of all optical logic gates. And finally, I just give in one slide topic of the next seminar, which probably will be held in summer or autumn, we will see. Okay, first of all, let me start please with the method. Here, firstly, I will start with the two-dimensional problems. And as you know, there are presented typical waveguides. For example, this kind of waveguide, when the defect is proposed by removing one layer or number of layers, and we have strong confinement here in this defect region. This is another type of the waveguide, but physics is completely different in comparison to this structure. Here, the guidance can be realized only by resonance case. And when I say that this structure has two-dimensional, I mean that fields are invariant in the z-axis, so perpendicular axis with respect to the screen. However, during this presentation, I will show you how this problem can be generalized for the three-dimensional case. Okay, the modal field is represented as a superposition of an infinite number of space harmonics. And this term here is very important. Here is a longitudinal wave number for each space harmonic, and this is actually complex wave number. So alpha is called the attenuation constant, or the complete imaginary part of the transverse wave number, and beta is the propagation constant. Beta is different for each space harmonic, and alpha is the same, and is actually the attenuation constant for this model. So our goal is actually to calculate efficiently this attenuation constant, because as I mentioned in the beginning, alpha unfortunately cannot be calculated using commercial software, but this parameter is crucially important, and I will show later why, as for the millimeter and microwaves devices as well as in optical. Okay, now the method I will use here and the details I will show is based on the Lattice-Sum technique combined with the T-matrix transition method. And I consider several layers or multi-layer single-layer structures. The method is highly efficient since the Lattice-Sum technique, and I will show the details how we calculate, are evaluated using the Ewald approach. This method actually allows us to give determination for each space harmonic, to give proper or improper determination for each space harmonic. And the radiative features of the cavities excited by a single source, that microwave and millimeter wave, can be explained in terms of the leaky-wave. And that's why this proper and improper determination, which can be given in this method, play a crucial important role here. Let me start here with the single layer. So we have single layer structure. So we have periodicity along the x-axis, and we use the Fokker mode expansion. And I omit many populations. Just I show here how the reflected field, for example, in the y bigger than 0, here the reflected field is expressed. So here is the P matrix. The P matrix is a transition matrix for when the scatterers have singular cross section. So the P matrix is expressed simply, and this is diagonal matrix. However, for the other shapes, we should calculate it numerically. And here L is the Lattice-Sum matrix, which is expressed as the superposition of the cylindrical waves of cylindrical functions, particularly the Hankel function.
So in which basis do you write the matrix? Is it in the basis of different diffraction orders?
Yes, here, for example, P matrix, I calculate, for example, it depends how many phase harmonies are you taking into account. For example, the most important for me is that we should have convergence of this matrix. So it depends on the radius of the matrix, of course, on the material. If radius is bigger, we should take into account the lots of phase harmonies in order to have convergence. In this case,
I'm sorry. Isn't it? It should be written in terms of
with here,
matrix.
Yeah, matrix. Yes,
It's not waveguides.
no, it's here.
So the matrix is
Yes.
and maybe I'm but what is R plus and what is A?
Here. Yeah. This is the amplitude of incident work.
AI is
Here, for example, firstly, we're considering single layer. So single layer, we have simple incidence of the plane waves and that's the reflection and transmission problem. Of course, when we have multi-layer structure, and I will show later, the problem is slightly different, and I will explain how. Here, we are calculating the transmission. Here, so delta is Dirac's delta function here, and here we have a very important term, KYN, which is the transfer plate number. And this transfer plate number, because we have squared here, it has a two-variable function. And here, the proper and improper determination of the space harmony should be taken into account. And I will give later what does it mean. Actually, here we have also T, this is transition metric, and L, which is the Lattice-Sum. The most difficult part here is the accurate calculation of the Lattice-Sum, which I should.
I'm sorry, but this branch of square root is isn't it usually taken in the upper half spaces?
Yes.
As a rule of thumb.
Yes. For example, you can calculate in the complex part. This one, K, Y.
I mean, there is no ambiguity in the taking which branch should be taken.
It depends. For example, now, okay, I will show later, but this is actually important. This fitted end space harmony for each space harmony. It can be proper determination or improper determination. Proper determination.
I mean, the answer is no.
Yes. But
every time you should take it in the upper half space.
Yes, but it depends for each space harmony. The problem can be generalized for the multi-layers. In multi-layer structure, what does it mean? It means that, for example, the plane waves, which are transmitted waves for the second layer, are the incident waves for which are transmitted waves for the third layer, are new incident waves for the second. So we have a recursive algorithm for the layer structure, and this recursive algorithm is based on the matrix multiplication. That's why even if we consider, for example, 1,000 layer or 10,000 layer, for example, using the MATLAB or Fortran commercial software, we can very easily in a few seconds calculate any, for example, very many number of the layers. So the multi-layer problem is purely based on the recursive algorithm. For this case, if we know reflection and transmission for each single layer, we can very easily calculate the generalized reflection or generalized transmission matrices for the multi-layer set. And it takes just a few seconds. Okay, let's go to the Lattice-Sum here. Lattice-Sum is presented as a infinite sum here, and h is the Hankel function of the vector here. When kx is a real value, for example, theta 0, here it is a real value. There are some methods which actually can calculate this kind of series numerically. For example, one of these is present here in this paper. When kx is real, it means that we have a strong confinement of the modes in this Directive region. However, when k is a complex system, so in this case, we should use different mathematical method in order to have a convergence of this kind of system. And here we use the Ewald approach, and we present this Lattice-Sum as a sum of spectral and spatial series. Spectral and spatial series. Let me start for the spectral part here. The spectral part is presented as the infinite series for each space harmony here. And the Gaussian convergence is actually guaranteed by the error function which is given. For both spectral and spatial series, we have the Gaussian convergence for this Lattice-Sum, even when we have the propagation right now as a complex. Here, again, just ask some questions. So, how do we split into spectral and spatial series? Is there any pre-connection? Usually, you have considered the integral. For example, from minus infinity to be some splitting parameter. Okay, I forgot to mention here. This is splitting parameter. You can present with two integrals. And we actually consider these two integrals. First integral and the second integral from minus infinity to the splitting parameter and plus splitting parameter to the infinity. This one. And the splitting parameter here, this should be properly chosen because here we have chosen the square of phi because in order to consider few terms for convergence, this splitting parameter now is equal to 1.77.
So you need to guess.
Yeah, but usually when we have not so high frequencies, it is some papers already published when splitting parameter can be taken, for example, square of pi, approximately 1.77. But it should be modified when we consider very high. It's like the modified and it's given by which should be. The spectral term here also, and again the Gaussian convergence we have for this spectral series here. Let me say a few words about this integral. Usually this integral, as I mentioned also, this is splitting parameter, this is fixed parameter. In our case, it's a square of pi, 1.77. And this integral is important because here, usually this integral can be very easily calculated using, for example, trapezoidal rule, or can be calculated using Simpson rule. But in order, and it does not take much time actually, but in order to further speed up the calculation process, we use actually the recurrence relationship. And this integral, in order to calculate this integral for any n, it is important just to know only two terms with 0 and third index, and then other indexes can be easily represented by this reconsidered relationship. Of course, despite the fact that it does not take much time actually using computer to calculate this integral, but in order to further speed up the calculation process, the recursive relation can be used. Okay, let me say a few words also about the space harmony, behavior of the space harmony, so the proper and improper determination of the space harmony. When we have for each,
the recursion is stable for parameters.
Parameter,
Yeah, I mean, is it stable? You show that it is stable for any parameters.
This integral.
Yeah, I mean, I'm asking about stability.
You are talking about this integral.
About the formula in the center.
Yes, here. Yes. For example, if we have, for example, current complex value, it depends just on the KH, this is normalized parameter, and splitting parameter. This is stable, yes. This is very old paper with mathematical derivation of this one. This is So
not your result.
no, this is not. But usually this integral can be easily calculated, but the figures actually doesn't make some big influence on the calculator in the modern computer, but just anyway, it can be also done. So the proper and proper determination here, for the proper determination, since we have this kind of dependence, proper determination is that the waves phase harmony is decreasing infinity, and for the proper determination, of course, we have some phase harmonies, it depends on frequency, can have improper determination and have exponentially growing at infinity. Well, later, when I talk about the design of some kind of antennas, this improper determination, of course, in this case, plays a very important role. Of course, we should compare this method with other methods in order to have actual say, in order to say that our result is correct. Since as I mentioned in the beginning, we can use commercial software to calculate the attenuation constant. We can, but it's not so good result, and accuracy we cannot generously. Actually, we are using here for series expansion method, which calculates it similarly using the approaches, of course, different, but this method can also calculate the attenuation and propagation costs. We here use the PML, and the structure is bounded by the PML here and here. The studies are given here in this case, but just I will show also later this the time of computation is actually quite large, not so small. First of all, I will start with this structure, and here I am comparing here the propagation constant. I mean its real part and its imaginary part for this single structure. In first, here in this slide, we take these elements as the dielectrics. So we have two dielectrics here. The parameters are given here, and here is shown the Brillouin diagram. Along the x-axis, we measure here the normalized propagation constant, and along the y-axis, we measure here the normalized frequency. The values of the attenuation constants are given here. Let me start with this gray zone. In this gray zone, we have two bound nodes, where it means that the attenuation constant is pure zero. And then in this bound region, we have the first closed top-band region. Yes. Sorry.
Is it result of human?
Yes. I
mean, you presented equation to solve this scattering problem. But you are presenting now solution of eigenvalue.
Yes.
My question is, how did you get eigenvalues?
Okay. Very good question. Let's start, for example, here. Here I present, for example, the second problem for the symbol. Here is kx0 we have, which is the x component of the, for example, this net value. But for this is technical. But for the guiding problem, we just assume that this kx is the pairwise propagation constant in the method, and we solve the eigenvalue problem. Yeah, this is very easy actually. For example, for the scattering problem, you need to define the angle of incident this one. And here we just assume that we have k0, and this should be fine.
Yeah, I mean, but you see, you solve kind of, you don't formulate this problem on your slides, right?
Okay, yes, yeah, you are correct. Maybe you slide to get it, but
usually eigenvalue problem is more complex to solve than scattering problems. Sometimes there are numerical difficulties to solve.
But for example, if we consider,
I understand. Okay.
Yeah, thank you. Yes, I agree. But for example, if we consider here, we have guidance here, and we have like scattering problems here, so we can actually very easily to review the scattering problem to the guidance and then solve the determinability.
I believe that for the eigenvalue problem, you have to find a complex value of k by factor, but how to find it? You have many ways how to do it and how to find roots this equation and how to evaluate how many roots. Maybe there are two poles in opposite sign which cancel out each other, and many other problems. This question is also of some interest for the in the audience.
But actually, yes, you're correct. For example, the eigenvalue problem for the when you consider, for example, propagation value as a with the root, for example, it can be easily solved just by calculating determinant when it's equal to 0. But your question is very important. Maybe a few slides are left here, just how we reduce from the scattering problem to the model analysis.
But you solve not matrix inversion. Because you have to find.
Yes. No, this is not
details. So my question is, which method do you use?
Actually, we have, if I can write it is right for this proposal. Okay, for example, here we assume that we have structure here 1, for example. This structure is characterized, for example, just reflection matrix, let's call reflection matrix 1. Here we have, for example, structure 2, and this is characterized by reflection matrix 2. And here, for example, we have some kind of, let us say that we have this Kx, which is actually complex value Q. In order to calculate this one, we are actually calculating, I should use this one here. I will say what is it, and this is determinant, and it should equal to 0. Here is the unit matrix, only diagonal elements are 1.
So you solve nonlinear equation to 0 the determinant.
Yeah, right. Yes.
So this computation is quite demanding.
Using, for example, I'm using actually Fortran and to solve this one, and it's you should find that actually Yes. Yes. And actually here W is related to this width of this structure. Here R is the, for example, the importance why I started with this scattering problem in order to calculate R here. R is a reflection matrix. For example, if we have 1,000 layers or I don't know many layers, it's quite challenging. It is function of course of Kx. And I'm solving actually this equation.
So may I ask a question? What the design? So I guess when you try to find the propagation of specific value of frequency, you get multiple loops. Some of them correspond to waves which are decaying fast. Some of them correspond to waves which decay not so fast.
No, for example, okay, thank you. For example, let us consider here this one. Actually, what is here? For example, actual unknowns are unknown is Kx real part and Kx imaginary. And for example, here we have completely, when I just calculate rigorously, R1, R2, W, here for this simple element, this is much simplified than this. But anyway, I am solving the determinant for this Kx here. And for example, in this group, I just obtain only solution when alpha is 0 and Kx some kind of, and beta is some kind of Kx. This is the boundary region, which is characterized with the attenuation completely equal to 0. Okay, then go to the bandgap. In this bandgap, as you know, here we can easily fix that. And only alpha is changed. Of course, you can start, for example, here in this region, both beta and alpha are changing some kind of values, and just we can easily, for example, use the second method. Mathematically, using second method, you can easily calculate beta and alpha.
Yeah, but just to elaborate on my question. So if you're working in the bandgap, can you have the situation when you have several waves which are decaying with different decay rates, several hours?
Yes, here. But here I'm considering alpha is bigger than that.
I mean alpha bigger than 0, so you get a process. You can get alpha equal to 1 is a root, and alpha equal to 10 is another root. Could that be possible?
Yes, it could be possible, but it depends. For example, when I start from here, I saw it, for example, here, we came here just to calculate here, alpha was 0. Then we are in the closed over. then here it means that alpha should increase. And I just follow this solution. I just follow the solution. If you are talking that this could be another model, which is of course I can find it as well, of course. But I just using the second method, I just follow firstly this region. And the next slide, when I consider the plasma, in this case, I also consider high. Here we have this.
All the similar. Consider structure with some material losses, some absorption. So you have the first question with no absorption. Actually, you have two branches, one from the right, one from the left, backward wave, and at the point of the coalescent, you have actually two modes, and which one you are following?
I'm sorry, which one?
You have coalescence of two modes, and after on the next frequency in the bandgap, you have two modes, and which one have you choose?
When you talk about band, you mean this, for example, this stop band region, or generally?
Yeah, stop band region.
Yes, it's stop band region. Yes,
Here, stop band region. Let me photo. Okay, I expect that you have something like this and this.
Yeah.
And here you have two bands, 1, 2. Here you have also 1 plus 2, and after that they are split by 1 and 2. And how when you go here, following the evolution, you go there, and from this point where they are coalescent, how do you choose which one? With positive or negative imaginary part?
Positive imaginary.
Okay, and at this point, how do you choose? It's just ad hoc procedure. You just know the solution, so you can predict which branch you should follow. Yeah, and do you consider an illustration when you have strong resonance effect, where you have something like this bandgap, gamma zone H. So you have something like this.
This is not this problem.
Yeah, I mean, if you consider something like, maybe like a chain of particles, or maybe even in such a structure, you can find a face with such agitation.
Yes.
And in this case, how to find the solution? Because as I remember, if I'm correct, something like go here, and after that go here. The real part, and the imaginary real part goes here, and in imaginary part it goes something like this, something heart-shaped form, or something like this.
I did not consider this problem. Maybe it should be checked. I cannot now respond correctly because I didn't start this problem. Yes.
Maybe one little more question.
Yes,
of course, you are solving this finding modes, you're solving this equation. And you have also a parameter of size of how many symmetrical harmonics you see. So my question is, am I right to understand that the convergence of modal propagation constants in your case should be exponential, or is it
equal? Yes. If I send you,
What is the rate of convergence?
If I understand correctly, you are talking about the size of matrix. Yes. For example, for this simple control, the size of matrix probably depends on the radius. So here, radius is not so small, it's so big.
Not radius, physical parameters, wavelengths to radius.
Yes, of course. Yes, of course. For example, here, for example, yes, the normalized wavelength is smaller. But actually, for this case, my calculation stops when determinant is satisfied with 10 minus 9.
No, it's not a question. It's
okay. It's
question of quality of the solution for a given size matrix.
Okay. For this calculation, actually, I did not change space harmonic depending on the region, which region I consider. I have taken the space harmonic number approximately 8.
How are you sure that 8 is enough?
Okay. I increased the space harmonics for example 9 and 10 and see do I have convergence, of course.
But my question was this, what kind of convergence do you have? Is it polynomial or exponential?
For the convergence, when actually I see the digits, first of all, I just calculate how the digits agree. For example, if digits agreement is with 7 digits, I can stop.
Okay.
Okay, and when we consider here, for example, the higher dimensions, of course, here the -1 space harmonics become improper and it's relative here. And here I am considering the similar structure, but we have here some kind of harmonic nature, the complex nature, so intrinsic loss of this epsilon here. And I compare this analysis with Professor Leviathan's analysis, where he solved this similar problem using Green's function directly. And of course, here maybe your question is, Maxim, that here we consider it fundamental and also higher orders here. And of course, the attenuation constant for higher order Gaussian should be separately calculated, and we can easily actually find both. In the previous slide, we calculated here, this is related only for the fundamental. Here, for fundamental mode and higher order mode. Here, and again, we have very good agreement between both methods here. Here I'm considering this comparison to the previous case, where the guidance was purely guaranteed using the resonance principle. Here we have the gap structure, one layer removed, and we have guidance here. For the 2 layers, it means that for the 2-layer structure, we don't have a strong confinement, actually. That's why we have here attenuation constant, and here we have the propagation constant. But in this here, if here is measured the normalized wavelength, and here is measured the propagation constant. Here is measured the attenuation constant. And here the 0 space harmonics becomes the actually the improper determination it has here. For comparison with the Fourier series expansion method, it took about 20 seconds for each frequency, whereas in our case it took approximately 0.0 seconds using the same computer software, the same computer of course parameters here. That's why it's quite fast when we solve when we use, for example, some kind of optimization problem.
So you comment that attenuation constants actually decrease with the increase of the number of layers. I understand this actually because the wave doesn't really does it decrease? Is the decrease exponential or why it should be exponential?
Yes, you have some kind of this. It approach 2 orders, because 1 2-order decrease here, and it depends on the frequency, of course. It depends on the frequency. Yeah, but still, in any case, it's kind of exponential. Of course, as you mentioned, when the layers are increasing, the attenuation constant is increasing, while the propagation constant almost doesn't show any change. Yeah. Yes.
Multiple theory is well suited for structure. But as I aware, 1 year function wave methods are more suitable for considering waveguide crystal structures and single effects, line effects, and so on. Are much faster and easier. Okay, I didn't get through the one-year function method at my time, but I have a colleague which made such a calculation for me, so I have no necessary by myself.
Thank you for your question. To be honest, I did not compare with actually the goal of this problem was actually to calculate the complex wave number. And actually, there are some papers, for example, which they solve the complex wave using the Dielectric ring function. I split many slides in order to show a relationship between the ring function and the Lattice-Sum technique. There is also a relationship. I did not compare with the method you mentioned, but actually it can be compared. But for this method, we actually, for each frequency, we need this kind of 0.02 second for each frequency. But it can be compared, but I didn't.
I already have answered.
Thank you. Okay.
Okay, when you want this?
Maybe some more general statement, because comparison of time for some particular example is not very representative. I mean, do you have a statement about maybe complexity of method, relation of complexities, parameters, or something like this?
Okay, then I should start from the beginning, just give a comment. First of all, certainly the advantage of the sum and first of all, what is simple here, when you consider, for example, multi-layer structure, you can very easily calculate the multi-layer structure regardless of how many layers, because it is based on the recursive algorithm. First, you can calculate as many layers as you want. Second, we take into account all space harmonies and interaction between the space harmonies.
Yeah, I mean, if you're talking about this recursive algorithm, you can see it contains matrix inversion, so the complexity is already n cubed.
Yeah, of course.
But if you compare with complexity of, for example, Fourier method, which we used for benchmarking, it has also complexity in cube. So generally, complexity is the same, but maybe you can make a statement about whether you need much less size of basis than other methods or something like this. And yeah, I'm asking about something to understand what is the general improvement.
Okay. If actually the method which I studied, and for this one is this one, for this series expansion. Here, we can also calculate the complex wave number because we have here PML and we can calculate. But the difficult here, first of all, is I spent some weeks in order to understand how the parameters of the PML first should be chosen. The thickness, the conductivity of the PML, this is difficult. Second one, this Fourier series expansion method needs to divide the unit cell here in some spaces, and it takes lots of time. That's why here, for example, in order to consider each unit cell here, we need some kind of staircase approximations to divide in this some space. Then it actually needs time. Whereas in the approach I proposed here, we consider this one as a just, for example, if we have circular road, just symmetrics, we can calculate. If you have another some kind of shape, there are two possibilities. We can easily calculate using the equal volume method or apply this one numerical. Which I studied actually, and I developed the code by myself, is this method. So it's because it can also calculate. I don't know many papers which can calculate fast or relatively complex wave number on this one, but this method started. But actually, difficulties, as I mentioned about, this is the difficult here. Because here the PML and also the staircase approximation for each unit cell. These are the disadvantages here.
Just a short one. So we have around 15 minutes left. So I believe you have an option to shut us up. Saying that you speak about 15 minutes.
Okay, it's very
So we will make these questions, but and you may think.
Yeah.
Yes, in this case, I think I present, first of all, I wanted also to show some kind of application in the optical region, but I think for the next seminar, maybe I will go into another topic. So I complete with this method and show its application on the millimeter wave region, and that's all. I think this is the best one here. So here actually we consider here how this analysis can be used for the radiation problem here. And here we can go to see in the previous slide I mentioned that for this guiding region, zero phase harmonics becomes improper and it's radiating in the air. It means that it can be used as an antenna for some kind of guiding device here. So I present here, for example, we have some source here and the source radiation. Actually, I omitted this slide as well, but when you see here, these structures above and below are periodic and only one source. So the complete structure is aperiodic. That's why I developed another method, which just proposed this source as an infinite series of the linear space sources and solve the whole problem as a periodic one. And then using the spectral domain, we can calculate the radiation problem. But I omit here this one. I compare here my method here and the leaky-wave approach. The leaky-wave is actually considered as the integral from the infinite aperture. There's a well-known formula developed just more than 20 years ago. Actually, to calculate the leaky-wave radiation when we have infinite aperture, it can be taken using the integral. I also have here. But why actually the knowledge of the complex wave number is very important? Because from the theory, we know that when the propagation wave number is very close, equal to the attenuation constant, you can have the broadside radiation. And the broadside radiation, very direct broadside radiation here in the vertical direction is very important here. However, when we have some kind of disagreement between propagation constant and attenuation constant, we have a typical leaky wave characteristic when we have same of this like not broadside radiation, but kind of scaling of infinity here. But still, we have a very good agreement between the results, which is based, of course, based on the method I proposed, and of course, beta and alpha calculated using the Lattice-Sum approach here, and using the leaky-wave analysis here. Here, actually, I truncated the structure, and during the truncation, I consider the size of this one, when of this whole structure, when the 90% of the injected power at the broadside frequency are radiated here. Since we have the truncated, I also use another method which solves the scattering and guiding problem for the truncated structure. This is called cylindrical wave approach. And I compare here three methods. Actually, the method I proposed here, the cylindrical wave method, and also CST microwaves here. And you can see here that for all methods, we have a very nice agreement here. But actually, when I use this method, of course, my method, which I proposed here, we can very easily calculate propagation constant, attenuation constant, and when they agree, in this case, we have a broadside radiation here. Then I go to the open waveguide analysis. After 3 slides, I finish. Then we go to the open in order to design the actual antennas. Then we go to the open waveguide structure. We have a line source here. The parameters are given here. We have, for example, 8 layers along the y direction. Since we have 8 layers, we have coupling between them. That's why we have 8 modes in the bound region, which appear here. Of course, we have the complex continuation of these modes in the radiative region, which are marked by red. But for the antenna design, it would be meaningless to take the frequency region here. Why? Because at the fixed frequency, of course, guided mode will be also excited. And when the guided modes are excited, it degrades actually the efficiency of the radiation system, for example, antenna. That's why we are working in a relatively high frequency, for example, here in this frequency, because we have some kind of backward propagating modes propagating, but here, and there is a small gap where only these modes, these two modes, were marked by red, are assigned. And they give very big contribution in the radiation here. But generally, this is not a scenario problem, of course, and it's quite difficult to choose the modes here. And since we have two modes, two improper determination here, two modes, we should calculate the residues and of course the quotient theorem. It means that how big is contribution of each improper determination here. And finally, we can choose the frequency and the radiation diagram is full here. The broadside radiation, very quite a directive radiation we have. Also, I have it not only, for example, dielectric structures when in free space, but also much more realistic structure when we have some kind of materials and we have some kind of hole. Really, experimentally, this is much more relative here, and here I'm calculating the bands actually, which are important actually to realize this structure, and I just compare these kind of structures. Both are periodic. Here is some kind of materials with drilled air holes, and here is the electric rods in different space, and compare the directivity. And it can be shown that when we put some kind of perfect electric conductor below and just don't allow energy to propagate below, just to have energy on here in the region, this kind of structure is much more effective because radiation is much higher here. And of course, the actual design, this student from university did this system with its light, actual design of this antenna. Yes, actually, I wanted also to go to the optical region, but of course, I think stop here. And finally, also, I should show this like a three-dimensional structure. The approach can be also generalized for this three-dimensional structure. This is maybe 2.5 dimensional structure. Let us go here. This is like a Woodpile structure, actually here. And this is not a two-dimensional problem. And this is actually widely used if you are reading the literature in the antenna problem. These Woodpiles are widely used as a substrate and superstrate for the antennas. The problem I propose here actually very straightforward for this kind of structure. What is important is just I consider firstly this kind of structure. This structure is periodical on x-axis. Then I consider this structure, which is periodical on z-axis. The multiple interaction between these layers also should be taken into account. Of course, rotation and field rotations also using the electromagnetic force. And finally, we can very easily multi-layer structure calculate here. And the formulas to get the reflection and transmission matrices for this structure. This is actually the structure where we can calculate the generalized the reflection and transmission matrices. And of course, your question, this problem is easily reduced to the guiding problem when we know the reflection and transmission characteristics of each layer. And here are some comparisons with the CSP for the radiating problem. However, now I am working for the modal analysis for this kind of structure and trying to compare in the bound region, because I cannot compare in the complex part, I cannot compare with any commercial software, but in the bound region, I am trying just to actually calculate this one. Okay, maybe next seminar I will talk about this because this is another different topic about this. Thank you very much.
Yeah, thanks for that. So let's take a look. We have some time for questions. I will start maybe with the general comment. Disclaimer, I'm not a specialist in numbers, but still we did some calculations. So I know that in console physics, there is so-called weak formulation, in which case you can resolve, you hit the frequency and define the propagation constant. And through you can find these complex propagation constants. That's what actually we did with students. It works. So I wonder how this compares with the peak. Could you comment maybe this is time demanding? So if you say something like that.
Okay. Thank you very much. I cannot say anything about the console, which the peak and the student and the Roman group each compared with CSP. For the CFT, we have very good agreement, and CFT is very strong also for the bound rows. When attenuation constant is 0, we have no problem, and actually absolutely no problem. But for the complex wave number, she couldn't get accurate results with CFT, and if she tries, it needs much more time. I don't know about console because nobody didn't work with console, but what I can say is that in CFT, the result was not accurate, and also it needs much time. Yeah, so after that, it's console I don't know.
Thanks. So, any other questions? Maybe can you comment on this before we come? Do something with that.
No, in my group, we are not working in Andrei. My experience. Yeah, but usually at least for the electric structures.
Well, yeah, it should not explain that there's only issue this time, so maybe it's more time than one.
But it's not, yeah. But in fact, this fixed frequencies having variable problems which might be interesting to see your benchmarking.
The efficiency thing.
Yeah, because it's quite efficient.
About console and eigen values and eigenfrequency. In console, you need to solve large high value matrix, and it's more efficient. Solve the strict equation, but not just because you need to large mesh and large elements in matrix.
You mean for the attenuation constant?
Yeah.
Yes. The same in CFT. I'm not familiar with console. I mean, CFT was also the it's the same for it's quite complex and tiny matrix, but not for bound modes. I think console same for the bound modes. In bound modes, it might be